A cinematic descent into the silent, frozen cathedral of deep space. A landscape where starlight arrives weakened and ancient, where time feels stretched thin, where gravity whispers in broken equations. The chapter opens with the camera drifting through an abyss untouched by the warmth of galaxies, slipping past voids so immense they swallow entire clusters, gliding along the edges of nameless structures that bend the rules of nature. The narration speaks in slow, resonant breaths about the human longing to map the darkness, to interpret whispers from the cosmic frontier. Then, the shift, hints of impossible signals, fractured shadows, and distant distortions that refuse to obey known physics. Anomalies, silent rebellions against the universe's supposed order. The tone swells into philosophical terror. What if the universe hides truths too vast for biology to comprehend? What if the laws of nature we cling to are temporary illusions? This hook establishes the cosmic dread and beauty of anomalies, phenomena not just unexplained, but unsettling, indifferent, and cosmically treasonous. In the long chronology of scientific awakening, most revolutions arrive quietly. They do not erupt with thunder or declare themselves with certainty. They appear first as artifacts in the margins, small discrepancies in data, subtle deviations from expectation. And in the vast, cold theater of the cosmos, where distances drown noise and time stretches like cooling glass, every anomaly begins as a whisper, yet some whispers grow into storms strong enough to reshape cosmology itself. The story of deep space anomalies began in this quiet manner, not with a dramatic discovery, but with a faint smudge of light on a photographic plate in the mid-20th century. It was captured at Palomar Observatory during a routine survey meant to catalog distant galaxies. A graduate assistant, scanning the plate under a dim desk lamp, noticed a slight distortion near the edge of a faint elliptical galaxy. It bent in an inexplicable arc, too smooth to be a defect, too symmetrical to be chance. It was set aside as a probable smudge, perhaps a hair or dust grain caught in the emulsion. And yet, when the same region was captured months later with better clarity, the distortion persisted. A background galaxy appeared stretched, warped by a gravitational force that did not belong to any luminous mass. It would take decades before this feature was understood as a gravitational lens, hinting at dark matter's invisible weight. But at the time, it was dismissed, an oddity, nothing more. In science, anomalies rarely shout. They recur, quietly, patiently. Years later, another tiny deviation emerged, this time in the cosmic microwave background, measured by early balloon-borne detectors lofted over Antarctica's frozen silence. The instruments searched for the primordial glow left from the universe's birth, a microwave fog spread almost evenly across the sky. Yet data revealed tiny rogue fluctuations, colder patches, warmer specks, regions with alignments too orderly for random quantum seeds. These were circumstantial at first: noise, atmospheric interference, the trembling of instruments in sub-zero winds. But as the technology matured, as COBE, then WMAP, then Planck mapped the sky with rising precision, the deviations hardened into statistical fact. Some fluctuations stretched in elongated patterns, as though shaped by unseen forces across billions of light years. A strange axis, later called the axis of evil, seemed to mark a direction in the universe, an unsettling suggestion that cosmic structure might not be as isotropic as the standard model demanded. Still, scientists hesitated. Instruments were recalibrated, algorithms rewritten, sky maps cleaned of foreground dust. But every refinement sharpened the same contradiction. The universe was whispering something that contradicted its own expected symmetry. Another anomaly surfaced unexpectedly in the early 21st century, carried by signals from the Sloan Digital Sky Survey. While constructing a three-dimensional map of galaxies, astronomers uncovered colossal structures that defied probability, a quasar group stretching billions of light years, galaxy walls too immense to form within the universe's 13.8 billion-year timeline, and supervoids whose emptiness seemed almost sculpted. One void in particular, later called the Eridanus supervoid, appeared colder than surrounding regions in the microwave background, a discordant patch where the universe seemed to sag inward, drained of matter. Some suggested that its scale was too enormous to arise naturally, too vast even for inflation theory to explain. Others suspected statistical anomalies. But the cold spot remained, fixed and unyielding. Between these discoveries, missions probing gamma-ray bursts uncovered flashes brighter than entire galaxies, emerging from improbable distances. Some pulses arrived in unusual sequences, bursts whose energies clustered in non-random patterns, suggesting unknown astrophysical engines at work. A handful of these signals displayed spectral features so unusual that teams wondered if cosmic rays or solar interference had tainted the data. Yet repeated detections, across different detectors and missions, confirmed their authenticity. The universe had mechanisms far more violent, far more unpredictable, than theory comfortably allowed. Around the same time, radio telescopes encountered their own quiet revolt. The discovery of fast radio bursts, millisecond flashes from beyond the Milky Way, was first presumed to be interference from terrestrial devices, microwave ovens, communications equipment. But as detections grew and patterns emerged, it became clear that these signals arrived from far beyond Earth, each one compressed into a burst too intense for known astrophysical processes. Some appeared to repeat. Others emitted dispersion measures hinting at plasma densities not mapped in any cosmic region. A few carried subtle frequency drifts that seemed almost designed. Astronomers resisted that implication and instead sought natural engines. Yet the enigma persisted. Scientific revolutions often coalesce, not as a single revelation, but as a pattern impossible to ignore. And so it was with deep space anomalies, distortions of distant galaxies, rogue temperature fluctuations, colossal structures violating formation timelines, gamma flashes from improbable depths, radio bursts too brief and too bright for comfort. Separately, each could be dismissed as noise, coincidence, instrumentation error. Together, they whispered a different possibility, that the universe may hide more than it reveals. In quiet corners of observatories, researchers began stitching these threads together. A lens that bent light too strongly might hint at dark matter concentrations, yet those concentrations appeared in places where models predicted emptiness. A cold region in the microwave background might reflect a supervoid, yet its scale defied the mathematics of cosmic evolution. Signals that repeated with uncanny regularity could be natural, yet their patterns were too tight for randomness and too structured for familiar astrophysical engines. None of these discoveries arrived with fanfare. There were no grand announcements, no immediate claims of new physics. Instead, they appeared in papers cautiously worded, filled with margins, caveats, and disclaimers. Terms like anomalous, unexpected, statistically significant deviation, and requires further study became quiet flags marking territory where physics began to unravel at its edges. Across decades, observatories played their part in this silent accumulation. Palomar captured the first distortions. Arecibo listened to impossible radio pulses. Hubble, with its drifting, sacred clarity, mapped galactic arcs that bent too smoothly around invisible masses. Chandra detected X-ray shadows that seemed to fall from nowhere. WMAP and Planck carved the cosmic microwave background with unparalleled resolution, each new layer sharpening the discordant patterns of the early universe's temperature map. Even deep beneath Earth, detectors buried in polar ice or salt mines recorded neutrinos from unknown origins, ghost particles arriving with energies so extreme they challenged expectations of how the cosmos accelerates anything. And then came the deep voids, regions of space where galaxies thinned, then disappeared, leaving stretches of darkness spanning hundreds of millions of light years. Their mere existence hinted at processes too delicate and too enormous for current theory. If gravity shaped cosmic structure, why did these regions appear so unnaturally empty? Why did surrounding galaxies cluster in patterns that resembled vast, invisible scaffolding? The voids became part of the anomaly timeline, another silent irregularity in a universe supposedly governed by uniform laws. Quietly, almost reluctantly, the scientific community began to recognize these anomalies not as isolated curiosities but as a collective whisper, a record of the universe's refusal to behave exactly as predicted. Each anomaly marked a node in a growing network of contradictions, a cosmic tapestry woven from the threads of the unexpected. Yet none of these discoveries carried the weight of immediate revolution. Instead, they formed a slow, dawning awareness that reality may be deeper than the models designed to describe it. That the universe's structure might be more ancient, more fractal, more intricately organized, or more chaotically stitched than previously imagined. That physics, even at its most elegant, may still be only a translation of a far older, more complex language. In this chapter of cosmic investigation, there were no sudden revelations, no triumphant declarations. There were only faint smudges becoming confirmed distortions, statistical anomalies becoming persistent patterns, signals once dismissed as noise becoming repeated cosmic signatures. History was being written quietly, etched into sky maps, calibration charts, and long data tables scrolling through observatory monitors late into the night. Deep space anomalies entered the scientific record as whispers. But whispers, repeated across decades, become difficult to ignore. And when the universe whispers long enough, it forces humanity to listen. There are moments in the history of science when the universe seems to lean closer, its vastness pressing against the fragile scaffolding of human understanding. Moments when familiar equations tremble, when long-trusted models flicker like unstable stars, and when the cosmos whispers something so discordant that even the most disciplined minds feel a shiver of unease. The deep space anomalies, once quiet irregularities at the fringes of data, eventually reached such a threshold. What began as faint deviations solidified into patterns too coherent to dismiss, too persistent to confine to instrument error. And suddenly, the universe stood before physics like an ancient riddle, calm, immovable, unyielding, waiting for minds to confront its defiance. The first true shock came from gravitational distortions whose magnitudes exceeded all expectations. As telescopes sharpened their vision, and as gravitational lensing maps grew more detailed, certain regions of space bent light with impossible strength. The curvature seemed to suggest the presence of mass thousands of times greater than what any visible structure contained. Einstein's equations had predicted how gravity should deform spacetime, yet these distortions required densities so extravagant that no galaxy cluster, no halo of dark matter, could account for them. In conference rooms lit by the glow of projection screens, researchers recalculated the curvatures again and again. Every result pointed in the same direction. The distortions were real, and they were far too strong. It was as though spacetime itself were folding along hidden seams, pulled by forces that did not match any known catalog of matter. Then came the shock waves from the cosmic microwave background. The subtle alignments, elongated asymmetries, anomalous cold patches, and temperature correlations stretching across billions of light years were not behaving like relics of the early universe. They seemed arranged, patterned, as though sculpted by influences outside the smooth randomness predicted by inflation theory. The standard cosmological model assumed a homogeneous, isotropic universe at large scales, yet the data insisted on something else. A cosmos with large-scale structures so coordinated they challenged the very assumption of uniformity. When the so-called axis of evil refused to disappear after multiple data cleanings, it became a symbol of scientific discomfort, a cosmic fingerprint whose meaning remained hidden. Beyond these temperature maps, enormous structures emerged from deep field surveys, structures far older and more extensive than cosmic evolution allowed. Walls of galaxies stretching across light years measured in billions, quasar clusters so enormous they defied the theoretical limits of gravitational assembly. According to established models, such structures should never have formed. Inflation would have smoothed them out long before the first stars were born. Yet there they were, rising like titanic scars across the observable universe, relics of a formation history that contradicted every simulation. Scientists, trained to question everything, including themselves, responded not with sensationalism but with caution bordering on disbelief. Laboratories conducted meticulous checks on sensors. Teams re-examined data pipelines down to the smallest correction formulas. Observatories recalibrated, upgraded, and retested. For months, even years, researchers considered the possibility that errors hid somewhere in the chain. a misaligned lens, a faulty receiver, a misbehaving cosmic ray filter. Entire arrays were accused of malfunctioning. Yet every reassessment produced a deeper, more startling clarity. The anomalies were authentic, and the implications were immense. Large-scale radio observations contributed their own disquieting contradictions. Fast radio bursts, those intense, millisecond-long flashes, arrived with dispersion signatures too extreme to reconcile with known plasma densities. Some of these signatures hinted at matter distributions inconsistent with standard cosmic maps. A handful of bursts showed frequency drifts so smooth, so deliberate, that natural explanations strained under their weight. The statistical unlikelihood of repeated, structured bursts left some researchers pale with concern. Not because the signals suggested intention, but because they hinted at astrophysical mechanisms outside the boundaries of established physics. Even the gamma-ray sky refused to cooperate. The brightest bursts arrived with energy ratios that strained the limits of known collapse models. A few bursts traveled across such extraordinary distances that their coherence demanded propagation mechanisms more stable than theory permitted. Theoretical frameworks struggled to explain how photons of such high energy could traverse intergalactic space without encountering expected attenuation. It was as though the universe, at these scales, operated under rules that textbooks had not yet imagined. The shock deepened with each new observation. Supervoids, the cold, hollow regions, displayed temperature deficits too severe for conventional explanations. If the integrated Sachs-Wolf effect were responsible, the voids would need to be so vast, so gravitationally influential, that their existence would fracture current cosmological timelines. Yet measurements pointed toward precisely such enormity. Researchers who had spent their careers mapping structure formation found themselves unable to reconcile these voids with any standard model. The universe was not merely strange at its edges, it was structurally rebellious. These accumulating contradictions produced an intellectual vertigo within the scientific community. Quietly, beneath the surface of professional restraint, a current of unease stirred. For over a century, cosmology had rested on the powerful foundation of general relativity and the standard model of particle physics. Together, these frameworks described a universe logical, coherent, governed by laws elegant enough to survive every challenge. But the anomalies suggested fractures, subtle, expanding fractures, where the elegance began to fray. Some deviations implied that space-time curvature behaved differently across scales, hinting that Einstein's equations, though magnificent, might be incomplete. Others pointed toward quantum fluctuations exaggerated to macroscopic proportions, contradicting the statistical calm expected after inflation. There were hints of superhorizon correlations, regions of space acting in concert despite distances too vast for causal contact. Such behavior bordered on the impossible. If true, it meant the universe carried memories of conditions predating the observable cosmos. The philosophical implications pressed heavily on the shoulders of researchers. If these anomalies were genuine, and evidence increasingly suggested they were, then physics itself faced a crossroads. Either the models were incomplete, or the universe harbored structures and forces beyond current comprehension. In the quiet spaces of observatories, after long nights of analysis, individuals felt the weight of that choice. The cosmos had always been vast and mysterious, but now it felt unpredictable, almost untamed. The cinematic shock of these realizations echoed through every discipline. In gravitational physics, the unexplained distortions hinted at exotic curvature, perhaps dark matter behaving in forms not yet theorized, or perhaps something more radical, modifications to gravity itself, deviations from Einstein's geometry at cosmic scales. In quantum cosmology, the CMB anomalies revived questions about the earliest fractions of a second, about the fabric of the inflaton field, about whether the universe's birth had been uniform at all. In astrophysics, the colossal structures challenged formation models, forcing simulations to their limits. What engine of the cosmos could sculpt a quasar wall spanning billions of light years? What primordial event could lay down such architecture? Every question opened a deeper chasm of unknowns. The universe was not simply strange. It was fundamentally inconsistent with its own expected behavior. Yet amid the shock, a profound sense of wonder emerged. The anomalies were not threats to physics, they were invitations. Invitations to widen the horizon of thought, to consider that the laws known today may be mere approximations of a deeper, more ancient order. The anomalies did not diminish the universe's beauty, they intensified it. Each contradiction glimmered like a crack in the cosmic shell, through which a greater truth might one day shine. Still, the disquiet lingered. For the first time in generations, physicists felt that the universe might contain regions where the known laws were temporary suggestions rather than rules. Places where space-time bent in ways no equation had predicted. Structures so immense that no model could explain them. Energies so fierce they bordered on the unthinkable. The shock was not loud. It was silent, steady, and absolute. A recognition that the universe, in its vast patience, had been revealing only the gentlest edge of its true nature. And now, through anomalies scattered across the sky like enigmatic constellations, it had begun to reveal something deeper, something that challenged the very foundation of physical law. Something that suggested the cosmos was not finished being understood. The search deepened not as a single expedition but as a slow, braided campaign. Telescopes, satellites, detectors, and equations all leaning in, like listeners pressing their faces to the glass of a vast and whispering world. Where the earlier chapters told of hints and reluctant confirmations, this chapter follows the instruments themselves as they extend humanity's senses farther and more precisely than ever before. It is a descent through layers of measurement, an unfolding of technical artistry, the cold clarity of spaceborne optics, the subterranean hush of neutrino vaults, the long, patient arrays of radio dishes tracing the sky. Each new observation arrived like a kerf in the dark, and every kerf revealed grooves that led deeper still. The camera drifts, first, through the glass of the great observatories. From the prime mirror of a space telescope, light arrives sharpened and patient, photons carried across eons, landing on detectors cooled to near absolute zero. Hubble's deep fields had once shown islands of ancient starlight. Newer eyes, with larger mirrors and infrared reach, began to peel back layers of dust and time. The James Webb-like instruments revealed galaxies in infant form, but even among those newborn worlds, patterns arose that refused easy categorization. Alignments and rotations that repeated across regions thought to be causally disconnected, mass distributions that curved light in manners misaligned with visible matter. Ground arrays, their dishes turned like ears at the ocean shore, recorded radio transients with temporal precision measured in microseconds. The Square Kilometer Array and its precursors catalogued thousands of fast radio bursts and faint, structured emissions, some repeating, others singular, each arrival a line in a ledger that refused to be tidy. Beneath the Antarctic ice, neutrino observatories listened for ghostly messengers. IceCube and similar instruments found particles with energies so extreme they hinted at cosmic accelerators beyond established catalogs, sources that sometimes mapped onto the positions of anomalous gamma emitters, and sometimes did not. Gravitational wave detectors, tuned to the subtle tremors of space-time, registered collisions and ripples that fit neatly into models of black hole and neutron star mergers, and occasionally detected signals whose origin stories blurred. Data streams multiplied, each new instrument supplied a different language of the cosmos: optical, radio, microwave, X-ray, neutrino, gravitational, and scientists learned to translate across these tongues, seeking consensus. Yet the more precisely the universe was measured, the more recalcitrant the anomalies became. Lensing maps with unprecedented resolution revealed arcs and distortions whose geometry required invisible mass in configurations the models did not permit. When dark matter halos were reconstructed from lensing data, some regions demanded halos too concentrated or too distributed to be explained by cold dark matter simulations. In other sectors, the inferred mass was diffuse, smoothed across volumes where simulations predicted clumping. Numerical cosmology, those enormous simulations that attempt to grow a universe from primordial ripples, stared back and found features that could not be reproduced without altering initial conditions or introducing exotic interactions. Temperature maps from cosmic microwave background surveys, refined through successive missions, kept their stubborn deviations. Small, elongated anisotropies persisted even after foregrounds and instrument systematics were painstakingly removed. Cross-correlation studies, comparing CMB features with galaxy counts, weak lensing surveys, and integrated Sachs-Wolf measures, produced tensions. Some cold spots aligned with supervoids catalogued by redshift surveys, others did not. In regions where a void could explain a temperature dip, the void had to be enormously deep and wide, so vast that their formation under conventional structure formation became implausible. The resulting paradox nudged researchers towards subtle, and sometimes radical, reevaluations. Perhaps primordial fluctuations were non-Gaussian at scales not probed before. Perhaps inflation behaved differently in patches of space. Perhaps unknown physics altered photon propagation across cosmic distances. Radio astronomy, once content to map galaxies and measure synchrotron halos, now confronted bursts and patterns that begged for new categories. Fast radio bursts, with high dispersion measures and sometimes precise periodicity, forced careful statistical work. Were these simply rare astrophysical engines, magnet-ars and collapsing compact objects? Or was there an overlay of plasma screens and intervening structure-modulating signals in ways not yet modeled? Polarization studies and scintillation patterns suggested complex scattering environments. In a few cases, FRB host identifications placed these sources in environments that could account for some observed properties. In other cases, host galaxies were unremarkable, and the bursts carried signatures that implied propagation through media with properties not present in mapped intergalactic space. Gamma-ray telescopes and X-ray observatories added another layer of discord. Some high-energy transients arrived with spectra and temporal evolution that taxed collapse models. Photon survival across cosmological baselines, how gamma rays avoid pair production against background radiation, implied either unexpectedly low intervening photon densities or mechanisms for regeneration that theory had not fully catalogued. When teams cross-matched gamma events with neutrino detections, coincidences were tantalizing but rare. Where matches occurred, they suggested astrophysical beacons capable of accelerating particles to energies that pushed the limits of standard acceleration scenarios. The synthesis of all this data required not only instrumentation but also new methods of analysis, machine learning classifiers to tease patterns from noise, Bayesian frameworks to weigh competing models, and cross-disciplinary pipeline teams that could harmonize radio timestamps with optical redshifts and gravitational wave triggers. Multi-messenger astronomy matured from ideal to practice, and with it came a sober realization. Anomalies that seemed isolated in a single band often gained new significance when viewed across wavelengths. A cold patch in the microwave could relate to a large-scale distribution of radio sources. A lensing excess might line up with an X-ray shadow and a deficit in galaxy counts. Patterns began to cohere into maps that suggested large-scale correlations, synchronizations of properties across distances that classical causality could not easily explain. Yet every suggested unifying interpretation found a fissure. Hidden matter, modeled as exotic dark sectors interacting weakly with baryons, could explain some lensing oddities but then produced signatures in galaxy formation simulations that did not match observations. Modifying gravity at large scales could alleviate certain anisotropy tensions but conflicted with precision tests within the solar system and with gravitational wave propagation speeds. Photon-axion conversion across cosmic magnetic fields offered a path for gamma-ray transparency, but required magnetic coherence and coupling strengths that remained speculative. Each proposed fix solved fragments of the puzzle and left other pieces out in the cold. The deeper investigation also exposed the delicate fragility of measurement itself. Systematics, those quiet biases and unglamorous calibration errors, lurked everywhere. Teams recognized that the line between discovery and artifact could be thin. Entire campaigns were devoted to tracing instrumental footprints and sky subtraction residuals. Yet after years of such scrutiny, anomalies remained. They were not artifacts produced by a single telescope or a single technique. They recurred across independent surveys, different wavelengths, and distinct methodologies. That repetition hardened the conviction that the cosmos, not the instruments, carried the signal. There was loneliness in this work, the kind forged by long nights analyzing faint datasets, by the patience required to wait for a rare event, and by the knowledge that the universe withheld its deepest secrets. There was also courage, a scientific patience that fashioned better detectors, wider maps, and more comprehensive theories. Teams proposed new missions specifically designed to probe the oddities, satellites to map polarization with greater fidelity, arrays to measure lensing across wider fields, detectors to chase the highest energy neutrinos. Plans for next-generation interferometers and all-sky monitors were drafted with a melancholic reverence, as if each instrument could be a torch held against the dark. Philosophically, the deeper investigation suggested a universe more textured than previously imagined. It raised questions about time, whether information could imprint across cosmic epochs, about existence, whether unseen fields or hidden sectors threaded the cosmos, and about origin, whether the primordial conditions were as simple and uniform as inflation predicted. The hunt had become not merely technical but ontological. Each new dataset reframed what it meant to infer causality at scales where light cones and horizon limits complicate narrative. As the chapter closes its slow descent, the view is not of a bottom but of another ledge. The deeper investigation had stripped away comfortable certainties and revealed a landscape of competing possibilities. It had multiplied questions even as it filled in maps. The instruments had shown both the universe's patience and its capacity to surprise. And in that tension, between the rigor of measurement and the poetry of the unknown, the scientific hunt continued. Telescopes recalibrated, missions planned, analyses rerun, all in the quiet confidence that the cosmos would, in time, yield more of its language to those dedicated enough to listen. A quiet crisis falls slowly over the cosmic sciences, not with alarm, but with the cold stillness of numbers that refuse to obey. In the dim glow of observatory screens, in the hushed corridors of research centers, the universe begins to whisper something unsettling. Patterns emerge where none should exist. Distances stretch into paradox. Ages drift beyond the horizon of possibility. And the familiar scaffolding of cosmology, the trusted equations, the calibrated certainties, begins to tremble. The camera drifts through a cosmic web of galaxies, their filaments stretching like ancient rivers of starlight. Yet even here, in the grand order of structure, something feels misaligned. Angles repeat across billions of light years. Clusters lean toward each other in coordinated defiance of randomness. Light bends as if pulled by invisible forces uncharted by dark matter models. In laboratories across the world, silence thickens. Data once dismissed as statistical aberration now returns with an almost deliberate persistence. The universe, long assumed to be indifferent, suddenly seems as though it is writing in patterns too vast for chance, or for comfort. This chapter enters the moment when curiosity turns into unease. When anomalies, once tolerated as minor imperfections in a young science, begin to converge into something older, deeper, and profoundly incompatible with the known laws of reality. A moment when cosmology itself begins to fracture under the weight of its own discoveries. Here, the mystery no longer whispers. It presses back. The universe has always spoken in silence, through faint photons stretched thin by cosmic expansion, through the slow drift of galaxies carried outward by the momentum of creation. For nearly a century, cosmology learned to translate that silence into equations, elegant, confident, self-consistent. Yet in the decades that followed the first discoveries of anomalous data, the silence shifted. It deepened. It thickened. It began to contradict itself. The camera slips through a galaxy cluster, each orb of light suspended in a dust-flecked sea. Their gravitational ballet should follow predictable curves described by Einstein's field equations. But as the lens glides along the outskirts, the choreography falters. Lensing arcs extend too far. Light bends more strongly than the known mass allows. Dark matter, the unseen anchor of cosmic structure, appears to overperform in some regions and vanish entirely in others. These inconsistencies were once isolated curiosities, brief shadows on the wall of observation. But as new telescopes sharpened their gaze, as deeper surveys mapped the universe in finer detail, the shadows merged into something dense and undeniable. Teams across continents reported gravitational distortions incompatible with lambda CDM, the reigning cosmological model. Some regions of space appeared too clustered, others too empty. In simulations, these patterns could be forced into existence only by rewriting parameters that were previously sacred: the density of dark energy, the curvature of spacetime, even the initial conditions of the Big Bang. For the first time since inflation theory unified early cosmology, the universe began to look uncooperative. The camera now drifts toward the cosmic microwave background, the afterglow of the Big Bang, a whisper from the universe when it was only 380,000 years old. Its temperature map, once hailed as the fingerprint of cosmic infancy, begins to fracture under scrutiny. Large-scale alignments stretch across impossible distances. A cold region spanning hundreds of millions of light-years dips in temperature beyond statistical expectation, and faint dips in polarization patterns refuse to blend smoothly into the standard distribution. Some anomalies can be explained by cosmic variance, the natural randomness of a universe too vast for complete uniformity. But not all. Not together. Not persistently. Scientists gather in conference halls with the manner of physicians confronted by a patient whose vital signs contradict the diagnosis. The instruments are checked, recalibrated, replaced. Satellites are reprogrammed, detectors cleaned, spectroscopy algorithms rebuilt. Yet the anomalies survive every correction, as if the universe is determined to insist on its contradictions. Whispers ripple through astrophysics departments. Is inflation incomplete? Is dark energy variable? Has gravity, the oldest force, been misunderstood in the deep cosmic field? Each hypothesis unravels as quickly as it is woven. Some require energy densities that violate quantum field theories. Others demand that space-time behave differently across different epochs. A few imply the existence of pre-Big Bang structures, relics from a time when the universe had not yet become a universe. The scene shifts to the Laniakea supercluster, its filaments stretching like a skeletal continent across the void. Here lies the Shapley Attractor, a gravitational behemoth whose pull reaches across hundreds of millions of light-years. Yet the motion of galaxies toward this region is stronger than models predict. Even accounting for dark matter, the velocity flows exceed theoretical limits. More troubling still, the movement seems coordinated with structures far beyond the local cosmic web, as if vast regions of the universe share a directional preference. Such alignments should not exist. Not in a cosmos born from quantum fluctuations, where randomness reigns supreme. Yet the lines persist, like faint scars crossing the fabric of reality. The emotional undercurrent deepens, not fear, but intellectual vertigo. In private notes, scientists confess an unsettling possibility. Perhaps the equations that govern the universe today are only approximations of a deeper, more ancient set of laws. Laws that the cosmos obeys only when it chooses. The camera descends into an interstellar void, a cavern of darkness stretching across hundreds of millions of light-years. Here, the loneliness is absolute. The density of galaxies falls to nearly zero. But these voids, too, bear anomalies. Some are too empty, as if matter was swept aside rather than diffused naturally. Others contain temperature fluctuations that seem orchestrated, not random, hinting at energy exchanges that standard physics cannot trace. Then comes the most unsettling pattern of all. Structures older than the universe as we calculate it. Quasars that shine in synchronized brightness patterns despite being separated by billions of light-years. Superclusters that appear too mature, too gravitationally relaxed for their estimated age. Galaxies whose metallicity suggests star formation histories tens of millions of years older than cosmological timescales permit. The anomaly is not merely spatial. It is temporal. The universe appears to remember something it should not. By now, the tone inside research communities has shifted. What began as mild academic discomfort grows into a quiet reckoning. Cosmology is the science of origins, order, and evolution, the story of how everything came to be. But if the anomalies are real, then the story is incomplete. The camera glides past the event horizon of a supermassive black hole, where space-time stretches to its conceptual limits. Here, the gravitational field is so intense that time slows, light spirals, and causality frays at the edge of meaning. To some theorists, the anomalies bear the same fingerprints, not local but cosmic distortions. As if regions of the universe behave like horizons of unknown phenomena, bending physics in ways that mimic black holes on impossible scales. Could the cosmos contain domains where space-time curls into topologies beyond our comprehension? Where inflation bubbled unevenly, leaving seams or folds that stretch across billions of light years? Where pre-inflation remnants cast shadows onto the observable universe? These questions, once fringe, now enter mainstream discourse. But the most profound escalation arrives from quantum statistics. Across multiple surveys, radio emissions from distant sources show correlations that cannot be dismissed as noise. Tiny variations appear synchronized, faint rhythms repeating across vast distances. Quantum randomness, the foundation of particle behavior, begins to look slightly patterned. Not deterministic, not predictable, but disturbingly intentional. If true, this anomaly strikes at the heart of modern physics. Quantum theory relies on the bedrock principle that certain events simply have no cause, that probability rules the smallest scales. Yet the universe seems to disagree in certain corners of the sky. It is as if reality, at its roots, harbors structures more ancient than chance itself. The chapter culminates as the camera pulls away from the cosmic web, revealing its filaments pulsing like a living organism, its structures echoing with impossible symmetries. The scientific crisis reaches its threshold. The anomalies are no longer curiosities. They challenge relativity. They strain quantum mechanics. They defy cosmological timelines. They imply ages older than the universe, patterns older than probability, and forces older than spacetime. In the deep silence of data, the universe offers no reassurance. Only a chilling suggestion. The laws of physics may not be universal. They may be regional, temporary, or incomplete. Cosmology stands on the edge of a revelation or a rupture. Here, the mystery does not deepen. When the universe ceases to behave, theory becomes refuge. Not certainty, never certainty, but a lantern held against the darkness. As anomalies multiplied across the cosmos, the scientific world turned toward its grandest ideas, those forged in the crucible of thought experiments and chalk-dusted classrooms. The camera glides through a quiet hall of equations, each symbol carved into the dark like constellations of human intellect. Here, the universe is not observed, it is imagined. Space-time stretches in slow cinematic arcs, revealing invisible geometries that curve and twist like tidal currents in a cosmic ocean. These are the landscapes of Einstein and Hawking, theories that describe reality not as a structure, but as a living fabric capable of bending, spiraling, and harboring scars from epochs older than time. Speculations rise like distant nebulae, beautiful yet unresolved. Cosmic strings vibrating through the early universe like primordial fault lines. Gravitational fossils, frozen memories from a pre-inflation state. Quantum fluctuations inflated into monstrous scales. Particles leaking from unseen dimensions. Domains of dark energy behaving like pressure waves beneath a restless surface. And, in the most daring thought, the faint tremor of other universes brushing against our own. Fleeting, cold, cosmically indifferent. Each theory attempts to hold the mystery in its hands, to sculpt meaning from defiance. Yet each also falls short, like tools too delicate for the weight of the cosmos. The anomalies endure, untouched by explanation. This chapter is a journey through the architecture of speculation, a cathedral built from mathematics, imagination, and the quiet desperation of a species reaching for answers the universe refuses to surrender. The search for explanation begins where the known laws end. When observations shatter established models, the scientific imagination expands to fill the cracks. What follows is not chaos, but a disciplined dream, a structured attempt to reconcile nature's defiance with humanity's insistence on understanding. The camera moves slowly through interstellar darkness, drifting between distant stars whose light has traveled billions of years to reach human eyes. But now that light is questioned. Its curves, its timing, its imprint, all begin to whisper of forces unaccounted for. To decode these whispers, scientists turn to the great theoretical pillars. Einstein's curved stage. Space-time unfurls like a vast fabric beneath the lens. Smooth, continuous, obedient to geometry, this is Einstein's universe, where gravity is not a force but a curvature written into the stage itself. Yet the anomalies demand deviations from this elegant script. Some propose warped space-time bubbles, relics from the universe's first fractions of a second. These bubbles, if they exist, would have formed when the cosmos was still young and chaotic, regions where the expansion rate differed slightly before smoothing out. Most should have disappeared, but a few might have survived, stretching with the universe, leaving behind subtle gravitational distortions. The camera glides across one such imagined bubble, a shimmering distortion against the cosmic web, bending light in ways neither dark matter nor general relativity can fully explain. Then comes the notion of gravitational fossils. These are the hypothetical remains of pre-inflation structure, imprints from a time before the universe underwent its rapid expansion. Like ancient bones trapped in rock, they would preserve patterns older than the cosmic age itself. If such fossils were real, they could explain the impossible alignments found across vast stretches of sky. But they imply something more unsettling, that the universe had structure before inflation, suggesting a prehistory for existence. Cosmic strings, fault lines in reality. The camera sweeps into a nebula, filaments glowing like cold embers. Through this stellar fog threads a thin, razor-straight line, an imagined representation of a cosmic string. Neither particle nor object, cosmic strings are hypothetical one-dimensional defects in space-time itself. Born from symmetry breaking in the early universe, they would be thinner than an atom yet heavier than a mountain, stretching across cosmic distances with perfect tension. If even one passed between Earth and a distant galaxy, it would create sharp gravitational lensing effects, sudden distortions, abrupt duplications of light. Some anomalies resemble these signatures. But cosmic strings remain elusive. No confirmed detection. Only whispers in data. Only the possibility that somewhere, in the deep voids, one might still drift. A fracture in the universe's architecture. Quantum fields unbound. The camera sinks into the quantum domain, an ocean of fluctuations shimmering like starlight on restless water. In quantum field theory, every particle is a vibration, a note in an invisible symphony. Normally, these fluctuations remain small, random, harmless. But inflation, the rapid expansion in the universe's infancy, stretched some fluctuations to cosmic scales. One explanation suggests that vacuum fluctuations amplified during inflation might have grown into the anomalies now seen across the sky. A tiny quantum tremor, magnified to the size of billions of light-years. It is a plausible idea. But the patterns are too sharp, too coherent. Randomness stretch does not create structure. Other theories point to exotic particles, candidates like axion-like fields or hidden sector particles emerging from supersymmetry. If such entities exist, they might interact gravitationally with the cosmos yet remain invisible to normal physics. Some anomalies hint at fields that subtly modify space-time curvature or influence the CMB's alignment. Yet without direct detection, these remain phantoms, ideas suspended between mathematics and possibility. Higher dimensions and leaking realities. The camera turns toward a black hole, its horizon cutting space like a shadowed blade. Here, in regions where gravity grows fierce, hints of higher dimensions become theoretically enticing. In certain models, gravity can leak into extra dimensions. If so, gravitational anomalies, those too strong or too weak for standard models, might result from unseen geometries wrapped around our universe. Some propose brain worlds, where our cosmos floats as a membrane within a higher dimensional space. If two brains drift close, gravity between them could produce distortions mistaken for dark matter or unexplained acceleration. More audacious still is the idea of bulk interactions, particles or fields slipping between dimensions, appearing as unexplained signals or missing energy in astronomical observations. Such ideas border on the mythic. Worlds layered on worlds. Realities brushing past one another like ghostly tides. The cosmos revealing only a fragment of its true architecture. And yet, for some anomalies, these models offer the cleanest mathematics. Dark energy, the restless sea beneath everything. The camera glides into the intergalactic void, where galaxies drift like embers on an invisible tide. Dark energy, the mysterious driver of cosmic acceleration, fills this emptiness. It is uniform, or so humans believed. But what if dark energy is not constant? What if it shifts, ripples, or condenses in subtle waves? Some anomalies, supervoid temperature dips, galaxy flow alignments, unexpected acceleration regions, point toward inhomogeneous dark energy, a universe where expansion varies slightly across space. Other models imagine false vacuum scars left over from early cosmic phase transitions. These scars could stretch across immense distances, warping space-time, creating the strange alignments found in the CMB. In these models, the universe is not calm. It is a restless sea. And every anomaly is a ripple from storms long past. Multiversal echoes. The camera ascends above the cosmic web, revealing a lattice of galaxies glowing like neurons in a grand, cosmic mind. Then, beyond it, darkness, an ocean of silence. At the edge of speculation lies the most unsettling theory: interactions between universes. If inflation spawned countless bubble universes, as some models propose, then collisions or near misses could leave imprints on each other's cosmic backgrounds. Circular anomalies in the CMB, unexplained temperature gradients, or directional asymmetries could be scars from such ancient encounters. One model imagines gravitational waves frozen into the microwave background, echoes of a neighboring universe brushing ours during inflation. Another suggests that dark energy itself might be influenced by forces leaking from adjacent universes, altering cosmic expansion subtly but perceptibly. These theories border on science's philosophical frontier, where equations brush against metaphysics. Yet they arise not from fantasy, but from attempts to reconcile data that refuses all lesser explanations. The universe may not be alone. Its anomalies may be its conversations. Insufficient beauty. The camera drifts through each theory like a museum of cosmic imagination. Elegant constructs, mathematically exquisite, beautiful enough to inspire awe. Yet each fails in one critical way. The anomalies are too vast, too varied, too persistent for any single theory to hold them all. Cosmic strings explain lensing anomalies, but not synchronized quasar patterns. Gravitational fossils explain early structure, but not quantum statistical deviations. Higher dimensions explain gravitational leakage, but not the alignment of galaxy spins. Multiversal interactions explain large-scale asymmetry, but not localized distortions. Each theory lights one corner of the darkness. None illuminate the whole. And so cosmology stands suspended, not defeated, but humbled. The universe has offered clues, not answers. Whispers, not declarations. Fragments of a truth too large, perhaps too ancient, for any one theory to contain. The mystery remains intact, beautiful, and still unanswered. Across the vast, unlit ocean of the cosmos, humanity's instruments drift like fragile lanterns, small, trembling sparks cast against a darkness billions of years deep. They are the quiet listeners of the universe, machines built from the dust of ancient stars, engineered to chase whispers that nature seldom gives freely. Around them stretches a silence so complete that it seems older than time itself, yet within that silence lie the fingerprints of creation, the faint scars of vanished epochs, and the elusive patterns hidden within cosmic noise. The camera floats past the cold mirrors of a space telescope orbiting far above Earth, their surfaces catching the pale glimmer of starlight that left its source before civilization existed. Beyond them, arrays of radio dishes turn in slow mechanical arcs, listening for subtle fluctuations in the cosmic microwave background, temperature ripples no wider than a millionth of a degree. Each ripple carries a secret, the geometry of space-time, the contour of the early universe, or the residue of unimaginable forces once unleashed. Deeper still, beneath Antarctic ice, neutrino detectors lie submerged in a frozen world of perpetual night. They wait for particles so indifferent to matter that billions pass through every square centimeter of Earth each second, unnoticed and unbothered. But every so often, one leaves a faint trail of light, and that brief illumination becomes a message from realms unreachable by any other means. Together, these instruments form a constellation of human hope, small, temporary, yet determined. They stand at the frontier of the unknown, searching for signs that might explain the anomalies scattered across the universe. And though each device is fragile, the questions they are built to confront are not. Humanity's lanterns in the cosmic storm. The universe reveals itself reluctantly. Even the most powerful telescopes capture only fragments of its truth, faint glimmers, distant echoes, and vanishing signals stretched thin by unimaginable expanses of space-time. Yet every instrument humanity builds comes with a singular purpose: to take these fragments and assemble a clearer vision of a cosmos that refuses to stand still, refuses to simplify, refuses to surrender its origin. The camera drifts through the quiet corridors of an orbiting observatory. Sunlight spills across gleaming gold-plated mirrors, hexagonal petals arranged with mathematical precision. This is the realm of deep space telescopes, instruments that sift ancient photons from the static of eternity. Their detectors measure temperature anisotropies in the cosmic microwave background, variations so delicate that the difference between them is comparable to the warmth of a candle measured from the moon. These tiny imprints are relics of the early universe, evidence of density fluctuations, quantum irregularities, and the primordial seeds of galaxies yet unborn. In those minute temperature ripples persist the possibility of anomaly, patterns that do not fit standard cosmology, cold spots that challenge uniformity, alignment features that whisper of physics beyond the known. Telescopes such as these search for them relentlessly. They do not blink. They do not tire. They simply collect truth. Far below them, Earth-based instruments listen for a different kind of message. Aerial footage opens over sprawling radio arrays spread across desert plains, rows of metallic dishes raised like silver petals toward the void. They map hydrogen distribution on cosmic scales, track synchrotron emissions spiraling around magnetic fields, and sense faint polarization signatures that could hint at exotic gravitational waves or cosmic strings once stretched across the early universe. If any remnant of such cataclysmic structures survived inflation, radio observatories would be among the first to notice their distortions. Yet even these immense networks are only part of the effort. The camera descends through layers of rock and ice into the subterranean stillness of neutrino observatories. Here, the world's quietest rooms hold enormous tanks of ultrapure water or liquid scintillator. One unexpected flash, one delicate blue Cherenkov ring, is enough to confirm the passage of a neutrino carrying a memory of supernovae, black hole mergers, or primordial decay processes invisible to every other tool. These instruments exist in isolation, but their mission is shared, to test theories that attempt to explain the universe's most persistent anomalies. Some anomalies may arise from instrument limitations. Others may hint at new physics. The difficulty lies in distinguishing between the two. The narrative shifts to the cold steel of gravitational wave interferometers. Vast L-shaped corridors stretch for kilometers, their vacuum tubes gleaming under soft illumination. Laser beams race back and forth with exquisite precision, sensitive enough to detect distortions in space-time smaller than a fraction of a proton's width. These detectors, first tuned to listen for the cosmic collisions of black holes and neutron stars, now seek fainter, stranger signals, irregularities that could mark the passing of exotic phenomena, cosmic strings snapping, particle defects vibrating, or disturbances from higher dimensional interactions. Each detector is a monument to patience. Most days, they hear only the gentle hum of their own machinery. But the universe does not always remain silent. And when it speaks, even briefly, their vigilance becomes justified. Above Earth, satellites equipped with quantum clocks drift in serene orbits. These clocks measure time so precisely that even the mild tug of Earth's gravitational field leaves a detectable signature. Their purpose is more profound than navigational correction. They search for deviations in space-time curvature, minute shifts that might imply dark energy fluctuations, exotic fields, or unaccounted-for forces acting on a cosmological scale. The chapter broadens its scope as the camera glides toward the next generation of humanity's planned instruments. In darkened laboratories, prototypes of cryogenic detectors sit suspended on vibration-isolated platforms, cooled to temperatures near absolute zero. At such extremes, the slightest interaction, an axion conversion, a dark photon scattering event, or an ultralight boson resonance, becomes theoretically measurable. These devices aim to reveal the phantom particles hypothesized to influence cosmic anomalies, particles that evade colliders, slip through detectors, and influence the architecture of the universe without ever interacting directly with ordinary matter. The narrative turns toward vast international projects. Proposed interferometers, tens of thousands of kilometers long, stretch across orbital diagrams like delicate lacework around Earth or the Moon. These future instruments could detect gravitational waves impossible to sense from the ground, slow, vast distortions produced by supermassive black hole in spirals, cosmic string vibrations, or relic gravitational waves from the earliest microseconds after the Big Bang. If such signals exist, they may provide the only direct evidence of pre-inflation physics. Humanity's scientific tools become characters themselves, guardians of the threshold between knowledge and mystery. Each one pushes against the limits of known physics. Each one tests the foundations of cosmology. And as the camera glides past them, their fragility becomes clear. A single misalignment can warp an entire dataset. A temperature fluctuation can mimic a false signature. A stray particle of dust can cast a misleading shadow on a million-year-old photon. Yet the anomalies persist. Cold regions in the microwave background that resist explanation. Large-scale alignments of quasar polarization vectors. Deviations in cosmic expansion measurements. Neutrino mass irregularities. Gravitational wave backgrounds that do not perfectly match theoretical predictions. These are the riddles that inspire new instruments, new missions, and new visions of the scientific frontier. The chapter closes with a slow, drifting shot of Earth from orbit, quiet, illuminated softly by the sun. Around it, satellites shimmer in their trajectories, each one carrying instruments of exquisite sensitivity. Beneath its oceans lie arrays listening for neutrino whispers. Across its deserts and mountaintops stretch telescopes absorbing starlight older than life itself. Humanity's lanterns, though fragile, hold firm. They face a cosmic storm of uncertainty with unyielding resolve. They do not yet know what the anomalies signify, new physics, hidden symmetries, or the deep imperfections of an emerging species learning to see. But they continue to observe, measure, listen, and wait. For in the silence between signals, the universe prepares its next revelation. In the final quiet of the cosmic journey, the universe opens into an immense stillness. Its galaxies drift like slow-moving lanterns above a sea of darkness, their ancient light whispering through the void. In this calm expanse, the anomalies that once ignited fear now hang like half-formed constellations, enigmas carved into the fabric of space-time, waiting with the patience of eternity. The camera glides through nebular threads that shimmer with soft, spectral blues. Dust clouds rise and dissolve in delicate spirals, each grain a survivor of forgotten stars. Beyond them, the glow of distant superclusters forms a faint web across the sky, an architecture so vast it seems to hum with a music no instrument could play. Here, in regions untouched by stellar winds, silence becomes almost physical. It wraps around the narrative like a thin, cold veil. The anomalies remain unblinking, voids deeper than cosmological models allow, gravitational distortions with no visible source, frozen imprints on the cosmic microwave background that should have faded long ago. They drift in the distance like quiet markers of a truth just beyond human grasp. Yet within this stillness lies something profound. Not despair, not dread, but a kind of humbling serenity, an acceptance that the universe is not a puzzle to be solved in a single era, but a manuscript written in the slow hand of cosmic time. The known universe, once charted with confident lines and elegant equations, now appears more like a coastline seen through fog. Every new observation extends the boundary, only to reveal more mist. Each anomaly acts as a subtle tide pulling the shore into new shapes. The structures older than predicted, the alignments too vast to arise from chance, the improbable symmetries scattered across billions of light years, all of them trace the outline of something larger, older, and stranger than any cosmological map has drawn. As the cinematic lens drifts past a field of dying red giants, their surfaces trembling in their final instability, there is a quiet reminder: even stars surrender their certainty. Their endings scatter the elements that build new worlds, new atmospheres, new possibilities. In their demise, there is renewal. So too with human understanding. The anomalies do not break science, they awaken it. They illuminate the fragile bravery within a species determined to understand the darkness from which it emerged. For every contradiction, scientists respond not with resignation, but curiosity. Not with fear, but determination. They sharpen their instruments, refine their models, and return to the void with deeper patience. Across Earth, telescopes sweep upward like metal flowers turning toward the sky. Gravitational wave observatories listen to the quivers of space-time, their laser arms stretched in silent anticipation of signals never before recorded. Deep beneath Antarctic ice, neutrino detectors wait for the rarest particles, ghosts that pass through planets as if they were made of nothing at all, to whisper their stories. And still, the anomalies linger. Uncooperative, elegant, indifferent. Some may be relics from a pre-inflation epoch, echoes of a time before time. Others may hint at hidden dimensions whose shadows graze the observable cosmos. Perhaps they are scars left by cosmic strings, or subtle disturbances carried from regions beyond the horizon of light. Maybe they are patterns written by physics not yet born into human understanding. Yet the universe does not mock inquiry. It simply is. Floating beyond a silent supermassive black hole, the frame reveals a ring of incandescent gas spinning with impossible fury around a throat of pure shadow. The gravitational tides distort starlight into shimmering arcs, bending reality into an ethereal halo. And even here, where the known laws of physics tremble under extremity, the anomalies remain untouched by explanation. They exist not as warnings, but as invitations. Questions, etched into starlight. The camera drifts further outward, leaving galaxies to shrink into tiny beads scattered across a canvas of infinite night. Cosmic filaments form a delicate lattice, thin as smoke yet spanning the visible universe. Between them, voids expand with quiet confidence, as though carving room for truths not yet imagined. In these vast pockets of emptiness, uncertainty becomes a companion rather than an adversary. The boundaries of knowledge soften. The edges of reality blur. What once appeared as defiance, data contradicting theory, structures defying age, now seems almost like guidance, leading thought toward horizons still uncharted. Humanity stands at the shoreline of this immensity. Its instruments are small, its reach limited, but its questions stretch farther than any starship ever could. Every anomaly, every misfit measurement, every impossible symmetry testifies to a simple fact: the universe is not finished revealing itself. And perhaps it never will be. For within the cosmic silence lies the quiet truth that understanding is not a destination but an evolution. Reality unfolds with the slowness of drifting galaxies, revealing only what curiosity has earned. Each generation moves the lantern of knowledge a little farther into the dark, illuminating edges that dissolve into deeper shadow. Near the end of the chapter, the camera drifts across the face of the cosmic microwave background, the faint afterglow of creation. Its mottled patterns pulse softly, like the heartbeat of the universe frozen in ancient light. Embedded within these patterns lie the anomalies that ignited an entire scientific reckoning. Cold spots too deep, alignments too straight, fluctuations too coherent. They stretch across the cosmos like fingerprints of something older than the birth of spacetime itself. A gentle reflection emerges. Perhaps these anomalies are not errors to be corrected, nor threats to physical law. Perhaps they are reminders of cosmic humility, proof that even the universe carries memories of origins it no longer fully reveals. As the narrative softens into its closing silence, the camera glides once more into an ocean of stars. Their collective glow forms a faint ribbon across the void, like a promise whispered into eternity. The darkness between them feels less like emptiness and more like possibility. The final reflection rises like a slow dawn. The universe is not a completed story. It is a work still unfolding, one where each question deepens the next, each contradiction opens a new frontier, and each anomaly becomes a doorway to realms of thought not yet conceived. Humanity may be small, but its curiosity is not. Its instruments may be fragile, but its resolve is ancient. Its understanding may be incomplete, but its wonder is infinite. And somewhere in the vast and patient dark, beyond the reach of telescopes, beyond the age of galaxies, beyond even the silence between dimensions, the next discovery waits. For the universe always keeps one truth in reserve, waiting for the moment a curious species turns its gaze toward the light and dares to ask for more.